Let's take a look at an example of adding two numbers. Now, the reason why we're doing this is because we use algorithms every day, and you don't even think about it. A very common example is making like a peanut butter and jelly sandwich. It seems so simple, and we just kind of do it automatically. We do it without even thinking about it, but there are certain steps associated with that in order to make the sandwich. So here, we're just going to take a look at how we would add two numbers. So for our input, we are given some value m, and we're going to assume that it's greater than or equal to 1. And we're given two positive numbers that contain m digits. So we're going to denote this as some number a, which consists of digits am minus 1, am minus 2, all the way to a0. And then some number b, which is broken up into digits bm minus 1, bm minus 2, all the way down to b0. Our output is going to be some number c that also has m digits. So we would have Cm minus 1, Cm minus 2, all the way to C0, where C is going to be the result of A plus B, where we're just adding the respective digits. Let's take a look at the complete algorithm for adding two numbers. The first step is we're going to have a variable which we'll call carry, and this is going to be initialized to 0. This carry is going to be used whenever we add two digits, and if the sum is greater than or equal to 10, we need to take the 1 over to the next digit, the next place in our number. So this carry is always going to either have a 1 or a 0. So if the sum is greater than or equal to 10, we're going to set the carry to 1. If it's not greater than or equal to 10, then this carry is going to be 0. The next step is that we're going to have another variable, which we'll call I, and it's also going to be initialized to 0. We're going to use this I to keep track of exactly which place in our numbers are we trying to add. So for example, I being 0 means we're going to add the two digits from the ones place. I being 1 means we're going to add the two digits from the tens place. I is 3 means we're going to add the two numbers in the hundreds place, and so forth. The next step is where we're going to do this repetition structure. So we see here that we're going to repeat steps 4 through 6 as long as I is less than or equal to m minus 1. So remember that we're given some m that's greater than or equal to 1, and we have m digits, so digits 0, 1, 2, all the way up to m minus 1. So that's where we're getting this m minus 1. So as long as I is less than or equal to that number, we're going to repeat steps 4 through 6. If I ever becomes equal to m, then we're going to get out of this repetition structure. So let's go inside here and see what we're going to be doing. So the first thing we'll do inside this repetition structure is we're going to add the respective digits for some place in our numbers. So here we're going to have Ci. So this is, remember, C is going to have the sum of A and B. So Ci is going to be the specific digit at place I. And this value is going to be AI plus BI plus the carry value. So we're just going to add the two digits plus the carry value, and we're going to store that in Ci. The next step is now we're going to check to see, is that sum in Ci greater than or equal to 10? And if so, then that means we need to split our value so that the one part of it gets moved over to the next place in our addition. So what we'll do is we'll take Ci and subtract it by 10. So for example, let's say we have 12 as our result for Ci. So when we subtract it by 10, then Ci is going to be 2, and then carry is going to be 1. So this is the equivalent of carrying that 1 over to the next place in our number. Now if this is not true, so if Ci is not greater than or equal to 10, so it's strictly less than 10, we're just going to set carry to 0. So like I said earlier, carry is either going to be 1 or 0. So it's going to be 1 if Ci is greater than or equal to 10, and it's going to be 0 if Ci is strictly less than 10. And then the last step inside this repetition structure is that we're going to add 1 to I. And what this means is we're just simply incrementing I to say that we're going to go to the next digit in the two numbers that we're adding. So if we were in the ones digit, now we're going to move over to the tens digit. Then we're going to move over to the hundreds digit, and so forth. But that's the entire repetition structure. So once we get out of that, so whenever I does become m, we're going to set Cm to whatever the value of our carry is at that point. So whenever we get to m minus 1, so whenever we're trying to figure out Cm minus 1, the carry is going to be either 1 or 0. So if it's 1, we need to tack on that 1 at the very far left of our number. So that's what's going on over here. We're going to tack on that extra 1 at the end. Now if it's 0, we're tacking on an extra 0 at the end. There's no harm, no foul with doing that. We do have to make sure that if at the n-1 place that the c n-1 was actually greater than or equal to 10, we do need to move that 10 over, so this is how we take care of that. And then after we added all the digits, we need to print them. So we're going to print cm, cm-1, cm-2, all the way down to c0. So we're just outputting what the sum of a and b are. And then finally, we just simply end our algorithm by just saying the word stop. So we saw an example of an algorithm where we just add up two different numbers, or technically they could be the same number, but we're adding two numbers. It seems really simple. So why do we need an algorithm for that? It just seems like it's unnecessary to write out the steps for these trivial tasks. So I mean, if it's very simple, why spend so much time writing an algorithm? The key thing here is that when we write an algorithm to solve a problem, it's not for us to execute the algorithm. We're trying to get a machine to perform these tasks. And last time I checked, machines are not humans. They follow one instruction at a time. We need to have these tasks be done automatically. So we need to write these steps so that way we can tell a machine how to add two numbers or how to do some particular task. They can only perform one instruction at a time. So we have to make sure that we give them specific, detailed instructions. So what do we mean by that? Well, machines can't skip steps, and they can't assume anything. So when we add two numbers and we just say, well, if the digit is more than 10, we'll just carry the 1 over to the next digit. We just take that for granted. We do that automatically. We do it without really putting much thought into it. But a computer, it has to be given those specific instructions. We have to tell it, if this sum is greater than or equal to 10, subtract 10, carry the 1. And we do that by setting the carry value to 1, otherwise set it to 0. So computers can't assume anything. It just does everything exactly the way you tell it to. You may have heard the phrase that a calculator is never wrong. It's just that you gave it the wrong input. It does exactly what you tell it to do. If you tell it to do the wrong thing, it's going to do the wrong thing. So same thing is true for computers. It's going to do exactly what you tell it to do. So that's why it's very important to make sure that when you write an algorithm for a machine, not for you, not for your friend, but for a machine, that you give it very specific, detailed instructions that a computer can execute one line at a time, and so that way you give it all the steps it needs. Because if you miss a step, the computer's not going to know what to do. It's not going to guess. The computer does not have the ability to guess. We can guess, but computers cannot guess. So we need to eliminate the ability for a computer to guess because it's not going to do anything. So that's why we need these specific detailed instructions. Now there are some variations of these problems and algorithms that are worth considering. So for instance, there are some problems out there that just have no algorithmic solution. So like for example, let's say you were asked to find all the digits of pi. There is no solution to that because the number of digits is infinite. We can try to come up with the next digit, the next decimal place for pi, but we're not going to be able to actually solve that problem. There are problems out there. The point is that there are problems that just do not have a viable algorithmic solution. And there's not really much we can do for those types of problems. There are some problems where we do have a solution, but the solution is inefficient. It just takes too long in order to actually solve it. So these types of problems are what do we call brute force problems, or brute force solutions, where the only way we can solve it is maybe to try all possible approaches. Let's say, for example, like you're trying to hack an account. Horrible example, but we're just going to go with it. And the only viable way to successfully do it is to try all different combinations of letters, numbers, uppercase, lowercase letters, and special characters. Will you get the solution? Yes. You will eventually find the password, but it will take forever to do it. And this is a reason why you're told to use uppercase letters, lowercase letters, special characters, and all that. Because it just takes so long. Like if someone wrote a program to try all combinations, eventually they'll get it, but it may take years before they get the solution. So these are what we call brute force solutions. These are inefficient solutions for solving a problem. Now there are some problems there where we don't know yet how to solve that particular problem. There may be a solution, but we don't know if there is an algorithmic solution for a problem. So just to give you a couple of examples, visual recognition is one that's something that people are working on right now. Abstract reasoning, sophisticated language understanding. I mean, these are different types of problems where there could be a solution, but we just don't know just yet. And that's kind of what makes computer science interesting, is that we can take a look at these problems and maybe down the road there will be a solution for these problems. I mean, the whole point here is that we try to create an efficient algorithm for solving some problem. And then if we can encode it into a programming language, and then we can take advantage of the speed and processing power of a computer, we can automate this solution and then produce our results. I mean, this is what computer science is all about.